Let's imagine, just for fun, that the Drake equation is a rough approximation, a back-of-the-napkin sketch drawn by a very smart person in 1961 who needed something put on a whiteboard for the first ever SETI meeting, so the attendees didn't just sit there staring at each other. And now let's imagine, stay with me here, that the Fermi Paradox isn't actually a paradox. I know. You've seen the explainer videos. You've watched the animations with the little blue dots representing civilizations spreading across the galaxy. You've heard the dramatic music. The Fermi Paradox is a paradox because it highlights a sharp contradiction between the high statistical probability of extraterrestrial intelligence existing and the total lack of evidence for it. The universe is vast and ancient. Hundreds of billions of stars. Billions of years older than our sun, habitable planets everywhere. Advanced civilizations should have emerged, spread, colonized, and left unmistakable evidence all over the galaxy by now. And yet, nothing. Silence. The Great Silence, as astronomers actually call it. No signals. No megastructures. No alien Netflix recommendations showing up in our radio telescopes. So yes, on the surface, that looks like a paradox. High probability of aliens existing. Zero evidence of aliens existing. Contradiction. Paradox. Cue the dramatic music. Dum dum dum. Except, and this is the part one want to spend the next 20-odd minutes on, it's only a paradox if the probability is actually high. And once you start pulling on that thread, the Drake equation starts looking less like a formula and more like a very optimistic wish list. I'm not an astrophysicist. I'm not any kind of scientist. I hold an BSBA and an MBA in business, which qualifies me for exactly nothing in this conversation. I don't pretend to understand the math or the physics behind the universe at the level of the people who actually do. But I do have an educated opinion, thanks to years of watching Astrum, PBS Spacetime, Anton Petrov, Dr. Becky Smethurst, Neil deGrasse Tyson, Dr. Michio Kaku, and many others who are considerably smarter than me and considerably better at explaining why the universe is trying to kill us. What I do understand is statistics. And when you run the actual numbers, not the optimistic Drake numbers, but the honest ones, the Fermi Paradox stops being a paradox and starts being the completely predictable result of a very hard probability problem. Let's go. The Drake equation. What it is and why it's a start, not an answer. Frank Drake proposed his equation in 1961. He was trying to organize the first serious scientific meeting about the search for extraterrestrial intelligence, and he needed a framework, a way to break down the question, are there other civilizations out there, into smaller, more manageable questions. The equation multiplies 7 factors together: the rate of star formation in the galaxy, the fraction of stars with planets, the number of those planets that could support life, the fraction where life actually develops, the fraction where intelligence develops, the fraction that develops detectable technology, and how long those civilizations last. Multiply it all out, and you get an estimate of how many active, communicating civilizations exist in the Milky Way right now. It is, and I mean this respectfully, because it was genuinely brilliant for 1961, a rough approximation. A sketch, a conversation starter. Drake himself said as much. The problem is that somewhere between 1961 and now, it started being treated less like a framework for thinking and more like an actual answer. Plug in some numbers. Get a number back. Feel either hopeful or terrified, depending on your disposition. The issue is that several of those 7 factors are not really known. They're guesses. Educated guesses, in some cases. Wild guesses in others. And when you multiply 7 uncertain numbers together, the uncertainty compounds in ways that can make the final estimate off by a factor of, let's say, 1 billion, which is a fairly significant margin of error, even by the standards of cosmology. Your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should. As Jeff Goldblum would say, probably thinking about the Drake equation. Let's start where the equation starts. How many Earth-like planets are there? Here is where I want to refine the Drake equation rather than dismiss it, because the first couple of factors, the ones about stars and planets, are now actually pretty well constrained by real data, thanks to the Kepler and TESS space telescopes. And the picture they paint is both more and less hopeful than you might expect. The Milky Way contains somewhere between 100 and 400 billion stars. Best current estimate, about 250 billion. Most of them have planets. The Kepler survey found that roughly 70% of stars host planetary systems of some kind. Fine. Good. Lots of planets. Now here's where it gets interesting. The habitable zone, the band around a star where liquid water can exist on a planetary surface, sounds like a generous concept until you actually measure it. For a Sun-like star, the traditional habitable zone runs from about 0.95 to 1.67 astronomical units. That sounds like a decent range. But here's the thing. Venus is at 0.72 AU and Mars is at 1.52 AU. Both are either just inside or just outside that range, and both are completely uninhabitable. Venus has a surface temperature of 465 degrees Celsius and an atmosphere pressure 92 times Earth's. Mars has essentially no atmosphere at all, which suggests the real habitable zone, the zone where a planet actually retains an Earth-like atmosphere with Earth-like properties, is considerably narrower than the theoretical boundary. If you split the difference between Venus and Earth on the inner edge and between Earth and Mars on the outer edge, you're looking at a band roughly 0.15 astronomical units wide, centered on Earth. That's about 30% of the theoretical habitable zone. NASA's Kepler survey estimated that about 22% of Sun-like stars have at least one planet in the habitable zone. Apply the narrower zone correction, and you're looking at something closer to 7%. For those keeping track, this is footnote 1. Then you need the planet to be rocky, Earth-sized, and not a gas giant. That cuts another 70%. Then you need it to retain an atmosphere, which requires the right planetary mass for sufficient gravity, the right magnetic field to deflect stellar radiation, and a host star that doesn't flare too aggressively. That cuts another 90%. Then you need the right chemistry: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the CHNOPS elements that form the building blocks of amino acids, which actually aren't that rare, but still knock out another 50%. Run those numbers across 250 billion stars, and you arrive at somewhere between 10 million and 2 billion Earth-like planets in the Milky Way, with a central estimate around 230 million. Footnote 2. 230 million. That sounds like a lot, and it is. But here's the first moment where I want you to hold that number and resist the urge to immediately populate it with civilizations, because we haven't even started on the hard part yet. Life, may always find a way. But also, life finds a way to almost completely fail repeatedly for billions of years before it finds that way. The 5 times Earth nearly died. Here's a fact about Earth that doesn't get nearly enough emphasis in the "are we alone" conversation. Earth has experienced 5 mass extinction events significant enough to be classified as near-sterilization events. Not minor setbacks, not rough patches. Events that eliminated between 50 and 96% of all species on the planet. The Ordovician, Silurian extinction, 443 million years ago. 83% of species gone. Glaciation collapsed sea levels and wiped out most marine life, which at that point was most life, period. The late Devonian extinction, 375 to 360 million years ago. 75% of species, over a 20 million year period. Ocean anoxia, cooling, possibly impacts. Set back vertebrate development on land by tens of millions of years. The Permian, Triassic extinction, 252 million years ago. 96% of marine species. 70% of terrestrial vertebrates. Caused by the Siberian Traps volcanic event, the largest volcanic eruption in Earth's history, which pumped enough carbon dioxide into the atmosphere to collapse ecosystems globally. This one is called the Great Dying, and the name is not an exaggeration. It is the closest Earth has come to being reset to zero. Recovery took approximately 10 million years. Footnote 3. The Triassic, Jurassic extinction, 201 million years ago. 50% of species. More volcanism. More chaos. The silver lining. It cleared the ecological space that let dinosaurs dominate. The Cretaceous, Paleogene extinction, 66 million years ago. 75% of species, including every non-avian dinosaur on the planet. A rock approximately 10 kilometers in diameter hit the Yucatan Peninsula at roughly 20 kilometers per second and released the energy equivalent of 1 billion nuclear weapons. The sky went dark. The food chain collapsed. Now, here is the probability question nobody wants to sit with. Each of those extinction events had a survival rate for complex life lineages of somewhere between 4 and 50%. Multiply them together. The probability of any given lineage of complex organisms surviving all 5 events in sequence to eventually produce something capable of asking questions about the universe is somewhere around 1 in 10 million. Footnote 4. And that's before you add the biological filters. The jump from prokaryote to eukaryote, from a simple cell to a cell with a nucleus, took approximately 2 billion years and may have happened exactly once. The jump to multicellular life with complex body plans appears to have happened once. Sexual reproduction, which dramatically accelerated evolution, required specific conditions to stabilize. And the specific cognitive leap that produces language, cumulative culture, and technology appears in exactly one lineage out of millions of species that have existed over 600 million years. One lineage. Us. The clock is running, and it's closer to midnight than you think. Here is the second piece of your probability problem, and it's the one that tends to make people quietly put down their coffee and stare at the middle distance. Earth's habitable window is not infinite. Our sun, like all stars, is gradually increasing in luminosity as it fuses hydrogen into helium, and its core slowly contracts. It brightens by roughly 1% every 100 million years. That doesn't sound like much. Over geological timescales, it is catastrophic. At some point, current models suggest somewhere between 600 million and 1 billion years from now, the sun will be bright enough that Earth's oceans begin to evaporate. The water vapor creates a stronger greenhouse effect. The greenhouse effect accelerates the warming. The warming accelerates the evaporation. It becomes self-reinforcing. It becomes Venus. The conservative estimate for Earth's remaining window for complex multicellular life is approximately 900 million years. Footnote 5. Now place that against Earth's history. Life appeared about 3.8 billion years ago. Complex animal body plans, the Cambrian explosion, appeared about 540 million years ago. Technology appeared, in cosmological terms, approximately 30 seconds ago. We went from the Cambrian explosion to smartphones in roughly 540 million years. The remaining window is 900 million years. That sounds comfortable. It isn't, once you consider what it means for other planets. A planet identical to Earth in every respect, but orbiting a star that brightens slightly faster, or that formed 500 million years later, has a proportionally shorter window. The Cambrian explosion equivalent starts later. The technological threshold, if it's reached at all, gets pushed closer to the deadline. The margin for error between complex life develops technology and star gets too bright for complex life shrinks toward zero. Earth didn't just have the right location. It had the right timing. Both. Simultaneously. That is one big pile of probability wrapped with a whole lot of luck. The detection window. The calculation nobody runs. Here is where I want to introduce the argument that I think actually resolves the Fermi Paradox. Not with exotic physics, not with dark force theory, not with the simulation hypothesis, but with arithmetic. We have been broadcasting detectable radio signals into space for approximately 75 years, perhaps a bit longer, but for this discussion we'll use 75 as the base. That is our radio window, the period during which a sufficiently advanced civilization within 75 light-years of Earth could detect that something technological is happening here. The next question, how far is 75 light-years? When a Milky Way is somewhere between 100 and 180,000 light-years across? Well, To give it a simple math number, it is between 0.075 and 0.0417% of the Milky Way galaxy so far. That's not very far in universe-sized numbers. 75 years. Out of a universe that is 13.8 billion years old. Our radio window, as a fraction of the age of the universe, is 0.00000005. 5 billionths. That is the fraction of cosmic time during which we are detectable. Now, assume another civilization exists somewhere in the Milky Way. Assume they also have a radio window, a period during which they are broadcasting and potentially detectable. If their civilization lasts 1.5 billion years, and their radio window is similar to ours, say a few thousand years at most, their detectable fraction of cosmic time is similarly tiny. For us to detect them, or for them to detect us, our windows have to overlap. Both civilizations have to be in their radioactive phase at the same moment in cosmic history. The probability of two randomly distributed 75-year windows overlapping within a 13.8 billion year universe is approximately 1 in 184 million. Footnote 6. Per pair of civilizations. So, yes, the window of discovery is teeny tiny. And that calculation assumes radio detection. It doesn't solve the distance problem. The Milky Way is 100,000 light-years across. A signal from a civilization on the other side of the galaxy takes 100,000 years to reach us. If they sent it 100,000 years ago, their civilization may not exist anymore. If we reply, our reply arrives 100,000 years after we send it, by which time we may not exist either. A two-way conversation across the galaxy is not just technically difficult. It is, for all practical purposes, impossible within the lifespan of either civilization. One Earth per galaxy. The generous assumption. Let's be extremely generous. Let's assume that every galaxy, all 2 trillion of the observable universe's galaxies, produces exactly one Earth-like planet that develops technological civilization. 2 trillion civilizations. That sounds extraordinary. The universe is teeming with life. Contact is inevitable. Except, the nearest large galaxy to ours is Andromeda, at 2.5 million light-years. A signal sent to Andromeda today, at the speed of light, the absolute physical speed limit of the universe, arrives in 2.5 million years. A reply sent immediately arrives back in 5 million years. Our civilization has existed in its current technological form for roughly 10,000 years. We have no particular reason to expect it to last 5 million years, or 1 million, or even 100,000. For a two-way exchange with Andromeda to complete, both civilizations need to survive for at least 5 million years after initiating contact. Given what we know about extinction events, climate windows, and the general precariousness of complex life, the probability of that is, and I'm being generous here, not high. For galaxies further than Andromeda, billions of light-years away, the round-trip signal time exceeds the remaining habitable window of any Earth-like planet. We couldn't complete a conversation with them, even if we started right now, and both civilizations lasted as long as physically possible. Footnote 7. 2 trillion civilizations. 0 conversations. Not a paradox. Just physics and time, doing what physics and time do. The ocean problem. Intelligence without radio. There is one more filter that almost never gets discussed, and we will explore for a few, because I think is genuinely underappreciated. Not all intelligence leads to technology. The assumption baked into the Drake equation, and into almost every SETI discussion, is that intelligence inevitably produces technology, which inevitably produces radio signals. That chain has a specific prerequisite that is so obvious, it becomes invisible. Fire. Without fire, no metallurgy. Without metallurgy, no tools beyond biological ones. Without tools, no industrial processes. Without industrial processes, no electronics. Without electronics, no radio. Orcas have been observed teaching hunting techniques to their young across generations. That's culture. They have regional dialects. That's language. They demonstrate grief, play, and what appears to be theory of mind. Some researchers argue their cognitive capacity in certain dimensions approaches or matches human levels. Footnote 8. An orca with the intelligence of a PhD physicist, living in the ocean, cannot make fire, cannot smelt metal, cannot build a radio transmitter, cannot be detected from space, cannot detect us. If the dominant intelligence on an Earth-like ocean world is marine, and there is nothing in physics or biology that says it couldn't be, that civilization is permanently, completely invisible to every other civilization in the universe, no matter how long it persists or how sophisticated it becomes. Intelligence and detectability are not the same filter. Drake's equation treats them as one. They are not. Clever girl Jeff might say, watching an orca solve a problem that would stump most humans, followed immediately by the realization that we'd never know about them. So, is the Fermi Paradox actually a paradox? Let me bring this together, because I promise you an answer and I intend to deliver one. The Fermi Paradox rests on the premise that the probability of intelligent civilizations is high. High enough that the silence is surprising. High enough that absence of contact requires an explanation. But run the actual filters. Narrow habitable zone reduces Earth-like planets to roughly 230 million in the Milky Way. 5 near-sterilization events. Each independently had a 4 to 96% kill rate for complex life. Multiply the survival probabilities. Roughly 1 in 10 million chance of any lineage making it through all 5. Specific biological transitions. Eukaryotic cell, multicellularity, sexual reproduction, complex cognition, language, each of which appears to have happened once in Earth's history. A closing temporal window. 900 million years remaining for complex life, meaning any planet whose clock started later or whose star runs hotter never reaches the finish line. A 75-year radio window in a 13.8 billion-year universe. The probability of 2 civilizations' detection windows overlapping by chance. 1 in 184 million. Ocean intelligence. An unknown but potentially significant fraction of intelligent life that never becomes detectable regardless of sophistication. And finally, physics, the speed of light, the size of the universe, the lifespan of civilizations, the impossibility of a two-way conversation across intergalactic distances within any civilization's remaining window. Stack those filters, multiply those probabilities. What do you get? You get a universe in which intelligent, technological civilizations may have existed, may exist right now, somewhere, but in which contact between any two of them is so improbable across both space and time that its absence requires no dramatic explanation whatsoever. The silence isn't a paradox. It's the answer. We are, almost certainly, not alone in the history of the universe. We are, almost certainly, permanently, and completely isolated from every other intelligence that has ever existed or ever will exist. Not because of a great filter ahead of us. Not because advanced civilizations destroy themselves. Not because aliens are hiding behind the moon. Just because the universe is incomprehensibly large. Time is incomprehensibly long. And the chain of events required to produce a creature capable of asking the question is incomprehensibly fragile. Life may find a way. Just not anywhere we can reach, and not at any time we can overlap, and possibly not in any form that uses radio. Other than that, yes, absolutely, life find a way. Final thoughts, and more questions than conclusions. Frank Drake gave us a framework. It was a good one for 1961, with the data available in 1961. The Fermi Paradox gave us a question. It was a good one too. But both were constructed before we knew how narrow the habitable zone really is. Before we had cataloged 5 extinction events that should have ended complex life on Earth multiple times. Before we understood the solar luminosity clock that is quietly counting down in the background. Before we had seriously grappled with the detection window problem, or the ocean intelligence problem, or the simple arithmetic of 2 75-year windows trying to overlap in 13.8 billion years. With all of that in the picture, the Fermi Paradox resolves, not with a bang, not with a conspiracy, not with a dramatic revelation, but with a quiet, slightly melancholy shrug. The universe isn't hiding aliens from us. It's just very, very big and very, very old. And the conditions required to produce something like us are very, very specific. And the window in which that something is detectable is very, very short. We are here. We are almost certainly alone in any practical, communicable, meaningful sense of the word, which is either the most humbling thought in the history of science or the most clarifying, possibly both. Either way, it's a Tuesday, and there's still a lot of universe left to look at. That's the episode. Sources are in the description. Go read them. They're worth your time. And if any astrophysicists are watching and I got something wrong, by all means let me know. I'm a guy with an MBA. My margin for error is, statistically speaking, quite large. See you next time.